Welcome AP Chem students to Unit 2, Ionic and Molecular Compounds, also known as bonding. Today we'll be talking about metallic and ionic bonds. So remember, the vast majority of the periodic table is made up of metals. Metals are all the things you think of as being metallic, that they are shiny, that they have a luster to them. Luster is your SAT word, meaning shiny. Most metals are a solid at room temperature, with the exception of mercury. Mercury is a liquid at room temperature, but every other metal produces a solid crystalline lattice at room temperature. Now, that crystalline lattice is very malleable. You can bend and shape metals. Metals are also ductile, meaning you can stretch them into wires. If you heat up a metal, it's kind of like silly putty, and if you were to pull on silly putty in both directions, you would end up with that stringy goo between your two hands as you pull it apart. Metals do the same thing. This property is known as ductility. So metals are ductile. We can stretch them into wires. Metals are also excellent conductors of energy, either in the form of heat or electricity. They're excellent conductors of heat because they form crystalline lattices, where the atoms of a metal form a lattice-like structure, the lattice being like that thing that's under your decking. And if you shake one end of the lattice, the other end shakes with it. If you were to kick your decking, that bottom layer would shake because they're all interconnected. When we heat something up, all we're really doing is providing it energy, and so it shakes. So when we shake or heat up one area of our metal, that energy transfers readily to the other metal atoms. Metals are also excellent conductors of electricity because of their structure. Metals form crystals because they readily lose electrons. Metals have extra electrons, and so they'll lose or share electrons into a giant pool of electrons, forming positive cations. These cations are suspended in a sea of delocalized electrons, meaning the electrons are owned by no one and they're free to move around. And it's this attraction for this sea of electrons that keeps the metal ions in place. Now, metals are excellent conductors of electricity because if you were to add an electron to this ocean of electrons, it'd be like filling up a cup that's already full. Any electron you add in is going to push one out, so energy readily flows through a metal's structure. Now, it is exceedingly rare for you to come across pure metals. Most pure metals have properties that are not always very desirable. For example, that ring on your finger that's made of gold, it is not made of pure gold because pure gold is extremely malleable. If it were, when you clap your hands, that force would be enough to deform your ring. So in order to give metals properties we look for, so in the example of your ring, of your jewelry, a little bit more rigidness, we mix in other metals, making what are known as alloys. Alloys are a mixture of two or more metals, and they come in two flavors. A substitution alloy is when we mix two metals that are approximately the same atomic radius. So for example, copper and zinc. Copper and zinc are extremely similar in atomic radius. Zinc is very resistant to oxidation, and so we mix these two together. We heat them up into a liquid, mixing them together to form brass. Brass gives copper that resistance to oxidation, the resistance to rusting, by filling in or taking the place a couple of the copper atoms. Interstitial alloys are formed when we mix elements that are vastly different in their atomic radius to give them different properties. So for example, iron is a very strong, dense metal. However, it is very easily oxidized by oxygen in the air. It also is extremely heavy. So we'll mix in some carbon to lighten the load and reduce the chance that it oxidizes. This is an example of an interstitial alloy in which iron this massive atom has carbon cations in between the iron cations. Iron and carbon have vastly different atomic radiuses, and so the huge iron atoms between each other have sufficient space for a carbon atom to fit in. The reason metals will readily give up those electrons into that sea of delocalized electrons is because they're trying to reach their lowest energy state possible. On the periodic table, elements in column 18, the noble gases are at their lowest energy state because they have a full s and p orbital. That full s and p orbital balances the attractive forces of the nuclear charge with the repulsive forces of the electron energy level. So elements will gain or lose electrons to have a full s and p orbital. Meaning metals, such as potassium with 19 protons and therefore 19 electrons, will lose 1 electron to have the same number of electrons as argon, to be isoelectronic to argon. And also, so like an element like beryllium with 58 electrons will lose 2 electrons to have 56 electrons, or be isoelectronic. By losing an electron, they develop a positive charge. Metals form cations. They lose electrons. Cations are similar to they have very similar properties. They conduct electricity and energy still. They just can't exist on their own. Having this positive charge makes them susceptible to being attracted to other things. Now, when a metal, like say lithium with 3 electrons, loses an electron to have the same number of electrons as helium, that electron has to go somewhere, and it's often picked up by nonmetals. Nonmetals form anions by gaining electrons. So for example, chlorine with 17 electrons is 1 electron away from that lowest energy state, so it will gain 1 electron to be isoelectronic with argon. Therefore, chlorine and the entire halogen family always form a -1 oxidative state. Anions are very different from their neutral counterpart. For example, fluorine is a yellowish brownish cloud that no matter what it touches, it oxidizes. It immediately catches it on fire. However, when it gains that 1 electron, it loses all that extra energy. Fluorine becomes fluoride. And now it's very different. Fluoride you brush your teeth with. So anions, we change their ending to "ide" because their change in energy levels is substantially different, and it causes substantially different properties for them. Now, when you have a positive and a negative, obviously they will attract to one another. This is known as an ionic compound, or salt in layman's terms. Ionic compounds form this repeating pattern where the cation is surrounded by the anion, and those anions are each surrounded by more cations. And the pattern goes on and on forever. However, when we talk about them, we wouldn't say that you have an infinite number of positive ions and an infinite number of negative ions. We instead write the simplest ratio of one to another. So in the case here, the simplest ratio in this picture of calcium to fluorine is 1 to 2. That simplest ratio is based off of how many fluorides it would take to balance out the oxidation state of calcium. Calcium develops a +2 charge because it's an alkaline earth metal. It is right here. Therefore, it has a +2 charge. Fluorine, a halogen, right here on the periodic table always develops a -1 charge on the -1 anion. So in order to balance their charges, you would need, for every 1 calcium, you would need two fluoride ions. And so the formula for calcium fluoride is CaF2. Now you can write the simplest ratio thinking of it mathematically. However, there is a shortcut to do this, known as the crisscross method. If you take the numerical value of the oxidation state, the number of the charge, and swap it with the opposite ion, you'll end up with the simplest ratio of one element to another, as long as you simplify. So for lithium and oxygen, oxide is always a -2 ion. So I'll take this 2 and swap it down and put it after lithium. I'll take the 1 and swap it down after the oxygen, giving me lithium oxide's formula of Li2O1. Aluminum is one of the transition metals. However, it's one of 3 transition metals you're responsible for knowing its charge. Aluminum always forms a +3 oxidative state. Oxide is always a -2, so when we crisscross, we'll take the 2 and put it after aluminum. We'll take the 3 and put it after oxide, giving us Al2O3. In both cases, notice that those are the simplest ratio possible. If they weren't, we would have to simplify them down. Such is the case here. Lead is a transition metal, and so I would tell you what the charge of lead is. In this case, we're dealing with lead 4, the 4 meaning that lead has a +4 ion. And oxide, again, is always a -2. So we'll take that 2 and put it after lead. We'll take that 4 and put it after oxygen. However, 2 to 4 is not a simple ratio. You need to simplify that down to 1 to 2, which is where we get PbO2. Lastly, you will notice that in every single case, I wrote the metal first. I always write the cation first because that's the rules. You always write the cation first because the least electronegative element always comes first in a formula. Cu2+, so cupric, and Cl is chloride. So we're going to take the 2 from chlorine and the 1 from chloride, and we are going to swap them. So CuCl. We're going to take that 2 and put it after the chlorine and the 1 and put it after the copper, giving us Cu1Cl2. Selenium is in the same family as oxygen. It's a chalcogen. It gets a -2 oxidative state. While nickel, a transition metal, again, I will tell you the charge. This is nickel +4. So when we crisscross these, again, the metal always comes first, so Ni and Se. So Ni, we're going to take that 4 and put it after selenium. We'll take that 2 and put it after nickel. However, 2 to 4 is not a simple ratio. We can simplify that down. So we need to simplify that down to 1 to 2. Sodium is an alkaline metal. Sodium always gets a +1 oxidative state. Sulfur is in the same family as oxygen, so it's always a -2 until I teach you otherwise. So Na and S, we can crisscross down. That 2 from sulfur comes after sodium, the 1 from sodium comes after sulfur, so Na2S1. This last example deals with a group of atoms together that have extra electrons, known as polyatomic ions. Some nonmetals form large groups with extra electrons. Polyatomic ions are things you have to memorize, and so I will be giving you a list of 18 polyatomic ions to memorize both their name, their charge, and the groups or the formulas. So for example, hydroxide is a hydrogen and oxygen that together have an extra electron. Or for example, phosphate. Phosphate is a phosphorus and 4 oxygens. Together they contain an extra 3 electrons. Or nitrate, lastly, is a group of nitrogen and 3 oxygens that together contain an extra 1 electron, giving them a -1 charge, which is what we see here. So the grouping of nitrogen and 3 oxygens together have a -1 charge. That's all of them together. So to balance out that charge with gold with a +3 charge, we would need 3 nitrates to balance out the +3 we get from gold. So when nitrate and gold get together, we get AuNO3. You'll notice that yes, I did not put the 1 after Au. Remember, as long as you write a symbol, the number 1 is understood. To show that nitrate together is that group of 4 atoms, we put it in parentheses to say these 4 atoms together have a -1 charge, and it takes 3 of them to balance out 1 gold. And no matter what the polyatomic ion is, you'll always view it that way. A group of atoms, it took 2 phosphates to cancel out the charge of 3 zincs. Naming polyatomic ions is very simple. You simply state the name of the ions present, because how many of each is irrelevant, because again, they form a lattice. So when we go to name ions, you simply tell me what ions are present. So in the case of Li2O, Li is lithium. Now lithium always has the exact same charge. Just by writing the word lithium, any chemist knows that lithium gets a +1 charge. So lithium, and then O is oxygen. However, this oxygen has formed an ion, so we call it oxide. So this is the formula for lithium oxide. Al2O3, Al is aluminum. And again, aluminum always gets the same oxidation state. It's always +3, so there's nothing to clarify here. O is oxide. Again, it's an oxygen that's formed an ion. So this is lithium. So this is aluminum oxide. Lead is different. Lead is a transition metal. It does not fall into the categories of elements with a known charge. Lead, right here on the periodic table, while in carbon's family, does not share an oxidative state with carbon. Lead can be +4, but it can also be +2. So how do you know which lead you're working with? Well, we state which lead it is in its name. So we say that this lead had a +4 charge by calling it lead 4 oxide. So we show the charge as a Roman numeral in between the cation and anion, because the cation, lead, can have multiple oxidation states. So again, we got that 4 from the oxidation state, from the charge of lead. So in problem 1, example 1, if we were to name these compounds, we would do so simply by grabbing our periodic table and stating which ions are present. CuCl2, Cu is copper. Copper does not have a known oxidative state. It's not in the first two columns. It's not silver, zinc, or aluminum, so we have to state what its oxidation number is. So this is copper with a +2 charge. So we call this copper 2 chloride. Nickel and selenium form nickel. Nickel does not have a known oxidation state. I have to provide it to you. So by saying this nickel had a +4 charge, we're going to call this nickel 4. And then selenium becomes seleniide. Sodium has a known oxidation state. Just by writing the word sodium, we know that it's always a +1 ion. So there's no point in writing the oxidation state. So we're just going to say sodium. And then S would be sulfur. So S becomes sulfide. So this is sodium sulfide. When it comes to polyatomic ions, all polyatomic ions have a known oxidation state that you had to have memorized. So NO3 is nitrate, and gold is Au. Now, gold is not in the first two columns. It's not silver, zinc, or aluminum, so I have to state that this is gold 3 to let you know which ion of gold we are working with. So when it comes to cations, group 1, 2, silver, zinc, and aluminum, you don't have to tell me their oxidation state or charge in their name. However, if the metal is not one of those, you have to tell me their oxidation state. So on page 13, you're given formulas. You have to write their name. So I gave you formulas, you write their name. If you're given the name, you write the formula. And that's just as easy as crisscrossing down. Silver is Ag, and silver is one of the ions you were responsible for knowing its charge. Silver is always a +1. Chloride would be chlorine that's formed an ion, so silver chloride would be AgCl. On the other side, Pb is lead. Now, lead is not silver, zinc, or aluminum, and it's not in the first two columns, so I need a Roman numeral here in order to tell me what type of lead it is. CrO4. CrO4 is chromate, the polyatomic ion, chromium with 4 oxygens. Chromate always has a -2 charge. If it took one lead to cancel out that one chromate, then lead must have a +2 charge. So this would be lead 2 chromate. Go ahead and pause the video, do page 13. Quick couple wrap-ups for ionic compounds. Ionic compounds as a whole, the salt on its own does not conduct electricity because that anion is extremely electronegative. It's going to attract electrons towards it. So if you try to pass an electrical current through it, while the metal ions would allow the salt to pass electricity through it, the anions will not. There's no mobile free ions in a salt's crystal lattice. However, if you take a salt and place it in water, water has a positive end. The hydrogen end of water is positive, and the negative end of water, oxygen's side, is able to rip an ionic compound apart. It attracts or surrounds their opposing sides. So the sodium ion in sodium chloride gets surrounded by the oxygen side of water. The chloride ion gets surrounded by the hydrogen side of water, and it's able to pull them apart. When you place salt in water, now you have this cation, this metal that is free and mobile and able to complete a circuit. This is known as an electrolyte. Metal ions in solution are called electrolytes because they complete a circuit. They are mobile and able to align to allow electricity pass through them. So while a salt's ionic form, the solid, is not able to conduct electricity, the dissolved form is. Ionic compounds are held together by electrostatic forces. They obey Coulomb's law. So if you have a salt made from sodium, a salt made from sodium chloride is a much stronger attraction than a salt made from sodium iodide. Iodine is so big, the force of attraction being proportional to the charges, in this case all the charges are the same, divided by the distance. This distance is much bigger than this distance, and therefore sodium iodide is a weaker attraction. It would take less energy to melt sodium iodide, to separate the ions from one another, than it would to melt table salt, for example. If you wanted to separate 1 mole of an ionic compound, that's known as its lattice energy. So again, lattice energy, very similar to melting point for a ionic compound, is most proportional to that force of attraction, which you can relate to the charges divided by the distance. Now, when it comes to electrolytes, salts can come in a couple different varieties. Some cations and anions have an extremely strong attraction for water, making them very easy to separate. And so therefore they form many ions when placed in solution. This would allow them to conduct lots of electricity. We call these strong electrolytes. Strong electrolytes produce almost all ions. When you place, for example, table salt in water, every single sodium ion separates from every single chloride ion. It is a strong electrolyte producing tons of ions in solution, and therefore a light bulb would be very bright, lit up with this setup. However, some cations have a very weak attraction for water. For example, lead. Lead, silver, and mercury, sometimes referred to as the heavy metals, they don't have a very strong attraction for water. So while a few lead and chloride ions might separate from one another, the vast majority are going to stay ions, and remember, are going to stay compounds. And remember, as a compound, they don't conduct electricity. So having only a few ions in solution means that a light bulb would be very dim. These are weak conductors of electricity, so we call these weak electrolytes. If something does not dissociate at all, we call it a non-electrolyte. These are normally things made up of all non-metals. For example, sugar. When you place sugar in water, sugar, all non-metals, does not dissociate from one another. This is a non-electrolyte. As a quick side note here, depending on how your professor is running this class, you might start talking about acids and bases here. Acids are when hydrogen behaves as a metal. It forms a positive ion. Acids can be strong or they can be weak electrolytes, but all acids are electrolytes in some way because all acids produce this hydrogen ion, which is mobile and free and able to complete a circuit. When your cations and anions dissociate from one another, it's known as a dissociation reaction. You start with a solid and then you place it into solution, normally water, so we'll symbolize it with an AQ afterwards to say that these ions are in solution. Fairly easy to understand. It just means we're going to separate our ions from one another. So for example, hydrocyanuric acid or hydrogen cyanide, we're going to separate the metals, in this case hydrogen, hydrogen from the nonmetals, the carbon and nitrogen, and return to them their charges. Hydrogen will form a +1 charge, it's a group 1 metal, while cyanide, the polyatomic ion, has a -1 charge. So let's write the dissociation equation for a couple of these. Sodium acetate. Sodium acetate can be written this way. The acetate ion is an organic compound, so we sometimes will write it as a structural formula, CH3COO. No matter how it's represented, the dissociation equation is to separate our metal ions from our nonmetals. Sodium is a metal, the acetate ion is a nonmetal, or is made up of all nonmetals. And again, we are forming ions. So sodium is a +1, acetate is 2 carbons, 3 hydrogens, and 2 oxygens that together have an extra electron, giving them a -1 charge. We could say that we started with a solid and then we put them into solution, and now we have them in an aqueous solution. So we could put an AQ afterwards. There's only one polyatomic cation that you're responsible for, and that is the ammonium cation. Ammonium phosphite, when placed into solution, is going to break up. We're going to separate our cations from our anions. Ammonium, again, is a nitrogen and 4 hydrogens that is 1 electron short, so it's a +1 charge. And phosphite is phosphorus and 3 oxygens with 3 extra electrons. We could say, we started with a solid, we ended up with something aqueous, but this problem's also missing something else. It took 3 ammoniums to cancel the 1 phosphite. So we need to make note of that when this breaks up, you would end up with 3 ammonium ions in solution. Another way to think of this is that there's a conservation of charge. There are 3 +1s and 1 -3. Overall, on this side of this equation, there's no charge, meaning on this side there needs to be no charge. So we have 3 +1s and 1 -3. So by having this 3 here, that cancels out our charge. Writing dissociation equations will become very important when we start talking about why I wrote this arrow going both directions. When we start talking about equilibrium, this will become a real important ability, the ability to write a dissociation equation. So towards that end, you can now finish page 13 writing the dissociation equation of some ionic compounds. Next time, we'll tackle the other type of bonds.